Hello and welcome to this video on simple harmonic motion. The definition of simple harmonic motion is that acceleration is directly proportional to the displacement from the midpoint and is directed towards the midpoint. What this means in practice is for a pendulum, the further out that the pendulum is from the centre, the more acceleration it has towards the centre. Acceleration can also be related to force due to F equals ma. So simply, the more acceleration is the more forces. So the further out the pendulum is from the centre, the more force there is pulling it back towards the centre. As a pendulum swings, their energy will be transferred between kinetic and potential energy. And whether it's a pendulum or a spring system, this potential energy will be either gravitational or elastic. A good way to think about this is with a graph like this. Badly drawn line. So if we say this point here is the midpoint, this is to the right of the pendulum, and this is to the left of the pendulum. Now, at the midpoint, it's going to have lots of kinetic energy, but no potential energy. And at either side, it's going to have lots of potential energy, but no kinetic energy. So what you can then do is draw two lines as so. This one here being kinetic energy, and this one being, we're saying, gravitational energy in this case. And at all points, GE gravitational plus kinetic energy equals the same. Because this assumes a system where there's no air resistance. It assumes a perfect pendulum where no matter how many swings it has, it always goes up to the same amplitude each time. No energy is lost. So the potential energy and the kinetic energy just get transferred between each other. Now let's think about the relationships between displacement, velocity and acceleration. So if we draw these as three graphs, this one will be displacement. This one can be velocity. This one can be acceleration. Now, these graphs make sense. At the highest displacement, there is no velocity, and there is the highest minimal maximum acceleration. Well, as said by the definition of simple harmonic motion, displacement and acceleration are opposite. They're directly proportional but in opposite directions. Now, if we think about the equations of these lines, the equation of this line is cos x, the equation of this line is minus sin x, and the equation of this line is minus cos x. Now, these actually, to get from that to that, you differentiate. To get from that to that, you differentiate. And this is showing a really key aspect of differentiation as well as simple harmonic motion and most types of motion, is that displacement over time equals velocity, and then velocity over time equals acceleration. Now, let's move on to the equations for simple harmonic motion. Firstly, let's remember that frequency has no impact on amplitude. You'll have if you have a pendulum and you swing it and displace it left a small amount and then measure how long it takes to swing, it'll take the same amount of time as if you raise it up a long way and then let it swing. They both take the same amount of time and thus have the same frequency. Now, acceleration goes as so. Acceleration equals minus 2 pi f squared x, where x is the distance, the displacement left or right from the midpoint. And thus, this can be the maximum acceleration will be when x equals a as the amplitude. velocity is plus or minus, because velocity is the same at either the minimum or at either as it's swinging past the midpoint in one direction or past the midpoint in the other direction. It is both the same maximum. The reason for 2 pi f is because it's equating kind of into radians, so that's just the reason for that being there. 2 pi f a squared minus x squared. These equations, depending on your exam board, you'll have to memorize them or you'll be given them in a data book. In my case, I was given them in a data book, which is lucky because they can be a bit difficult to remember sometimes. But for velocity, when x equals a, so when a displacement is at the amplitude, this goes to 0. If x equals a, this goes to 0, which makes sense because when it's its furthest point outwards, there is no velocity. And however, if x equals 0, then you have maximum velocity because it's a squared minus nothing. Now move on to displacement. Once again, use x as a signal for displacement. Is a cos 2 pi ft. And there we see here, for this one it's important to remember that when you're measuring this, the time is you're measuring the time past the start of the experiment. And at the start of the experiment, for this to work, you have to hit maximum displacement, because what it's effectively following is this graph here, where at t equals 0, if we say this axis is t, it starts at maximum displacement. And this effectively is what this equation here is relating to, or is explaining, is that graph. So the important things to recap over about simple harmonic motion is the definition, being that acceleration and thus force are directly proportional to the displacement from the midpoint and are directed towards the midpoint. The fact that the energy transferred between them is between kinetic and potential energy, and for a perfect system with no energy losses, the energies always equal the same. They always add up to the same amount because no energy is lost. Then the graphs between displacement, velocity and acceleration, and how effectively just differentiate from each other. And then the 3 equations, and obviously the fact that when you use x, that a either brings a maximum or when the system's at its maximum amplitude, x will equal a, and that will normally give a minimum or a maximum value for the equation. So I hope you found that useful. If you did find it useful, then feel free to subscribe to my channel, and hope you